We all learn about Newton's law of gravity in school. It's that famous formula that tells us why apples fall and how planets stay in orbit. And for, over 300 years now, it's felt like totally settled science. But what if I told you there's a giant mystery hiding in plain sight, right inside that very equation? A piece of the puzzle that's been missing this whole time.
What if the great Sir Isaac Newton himself never actually finished it? I mean, he left a critical part of the puzzle completely unsolved, a kind of placeholder that, for centuries, physicists have been able to measure but have never, ever been able to truly explain.
Okay, so to really get this, we've got to jump back to 1687. Let's take a look at what the brilliant Isaac Newton actually figured out, and maybe more importantly, what he didn't. We see this equation everywhere, right? Force equals big G times the masses divided by the distance squared. Well, here's the twist. Newton never wrote that G. That letter, the famous gravitational constant, it wasn't part of his original work at all. So, how in the world did he do it without G? Well, Newton's genius was all about connecting the dots. He took Kepler's laws about how planets move, he compared the moon's orbit to an apple falling from a tree, and from all that, he figured out the shape of the law. He proved that gravity gets weaker with the square of the distance, and he reasoned it had to be proportional to the mass of the objects. You see? He basically figured out the recipe, but he was missing the exact measurement for one of the key ingredients.
What this means is that Newton knew he had a relationship, a proportion, not a finished equation. He knew there had to be some constant, his word for it, a fixed number that would make the math work and turn that proportional 2 squiggle into a real equal sign. He left a blank space in his own law, a placeholder for the fundamental strength of gravity in our universe.
And that placeholder, well, that's the heart of our mystery. It's the number we now call G, and its true origin has been puzzling scientists ever since Newton first left that space blank. Get this. It took more than a century after Newton for someone, Henry Cavendish, to finally measure the value of G in a lab. And even today, while we can measure it with absolutely incredible precision, we still can't explain why it has the value it does. I mean, why isn't gravity just a little bit stronger or a little bit weaker? Nobody knows. So this brings us to the standard view in physics today. G isn't something that comes from a deeper theory. It's what they call an empirical constant. Now, that's really just a fancy way of saying it's a brute fact of the universe. We can only know what it is by going out and measuring it. It's a given, not an explanation. So on one hand, we have the standard view. G is a fundamental mystery we just have to live with. But then there's this alternative idea, the Harmonic Scale Framework, or HSF, and it makes a really bold claim. G is not fundamental at all. It says we can actually calculate its value from the very structure of the cosmos itself. So what is this Harmonic Scale Framework? How could it possibly explain something that has stumped physics for 300 years? Well, the answer it gives us starts with a completely new, kind of radical picture of our universe. At the very heart of the HSF model is this idea of a universal boundary. Now, it's not a physical wall made of anything. It's a real geometric structure, think of a slightly squashed sphere, that basically defines the container for our reality. The model then imagines a primary timing wave that travels along this boundary. The best way to picture it is like a steady, pure tone vibrating on the surface of a giant cosmic drum. This wave sets the fundamental beat, the clock rate for the entire universe. But here's the thing, this cosmic drumbeat isn't perfectly contained. The theory suggests that a tiny, incredibly precise fraction of that wave's energy leaks into the realm where we are, where all the matter exists. And HSF claims that it's this leakage of energy, this faint echo of a cosmic wave, that we feel and experience as the force of gravity. So in this view, G is no longer just some random magic number that we have to measure. It becomes the predictable, natural result of a physical process, the outcome of this cosmic clock wave. Right, so that's the core claim of the HSF model. G doesn't just exist, it emerges from a deeper cosmic mechanism. But how exactly would that even work? Well, the HSF model gives us a kind of conceptual recipe for G. It's built from 3 main parts. First, you've got the frequency of that main timing wave, the speed of the cosmic drumbeat. Second, there's the efficiency of the energy transfer, how much of that wave's energy actually makes it into our world. And third, there's a background link that sets the overall strength. According to this model, if you combine these 3 things, the precise value of G just falls right out of the math.
This completely reframes the entire question. The strength of gravity is no longer some fundamental, unexplained constant. Instead, it's an emergent property, an outcome of the universe's geometry and its underlying wave dynamics. It's not a rule, it's a result.
Now, look, this is a fascinating story for sure. But for an idea to be scientific, it has to be testable, right? It needs to make predictions we can actually go out and look for. So how could we ever prove or disprove the existence of a cosmic clock wave?
Well, the HSF model actually makes some very specific, though very difficult, predictions. First, it suggests that G might not be perfectly the same in all directions because of the shape of that cosmic boundary. It also predicts tiny, regular wobbles in gravity's strength as the Earth spins and orbits through space. And finally, it predicts a faint high-frequency cosmic hum, a direct signature of the timing wave itself that we might one day be able to detect.
And see, these aren't just philosophical ideas. They are concrete, physical claims. They give experimental physicists actual signals to go out and search for. And that is what moves this whole concept from just a cool story into the arena of real, testable science. Which leaves us with a pretty profound question. For over 300 years, we've treated the strength of gravity as a fundamental, unexplainable fact of life. But what if it's not? What if the force that holds entire galaxies together is really just the faint echo of a much deeper cosmic harmony? It seems this 300-year-old case is far from closed.